Let's see if we can figure out any other Laplace transform formulas. We have a Laplace transform formula that produces multiplication by the variable. So we have a Laplace transform formula where on the outside you have s times some other Laplace transform. So it seems like maybe for an idea for what we might try to calculate as a Laplace transform is a formula where you have multiplication by the variable on the input of your transform instead of on the output. So what I'm talking about here is Laplace transform of t times a function. Of course, since we don't have a formula for this yet, we have to use the definition. So integral from 0 to infinity of e to the minus st times t f of t dt. And it's hard to know what to do with this sort of thing. I mean, we're going to have to get this t somehow to be somewhere else so that we can express this as a Laplace, so that we can make the Laplace transform of f show up. But it's hard to know where this t might have come from. But, you know, in this example of multiplication by s, this came from having a derivative with respect to t on the inside, right, like this. This isn't quite right because there is supposed to be an initial value here. But this might make you think, well, maybe it was some derivative that made this t show up. So with that in mind, if you think about this entire expression and think, what sort of derivative might have made this t show up? This t could show up from the chain rule by differentiating this exponential by s. So, right, that might make you realize that, well, if we took e to the minus st times f of t, and we differentiated it with respect to s, well, this f of t part is acting like a constant multiple, so the derivative doesn't affect it. But then the derivative of e to the minus st with respect to s is minus e to the minus st times t, right? The chain rule spits out this minus sign and this t because we're differentiating with respect to s. But that's our integrand, except for this minus sign. So we can rewrite this as the integral from 0 to infinity of the negative of the derivative with respect to s of e to the minus st f of t dt. All right. Well, we have this derivative in this integral. It turns out that in most sane cases, so unless your function f is an extremely strange function, it's safe to move this derivative outside of the integral. This is because the derivative is with respect to s, but the integral is with respect to t. So in most cases, it's okay to interchange the order of the integral and derivative. Also, it's important that s doesn't show up in our bounds of integration here, which it doesn't. So we can move this derivative and this minus sign outside of the integral, and that gives us negative derivative with respect to s of the integral from 0 to infinity of e to the minus st f of t, but dt. But now this integral, that's just the Laplace transform of f. So we get minus derivative with respect to s of the Laplace transform of f, like that. So looking at where we started, right, we started with the Laplace transform of t times f, and we got minus derivative with respect to s of the Laplace transform of f. So it looked like this multiplication by t in the t world gives you a derivative in the s world, and also a minus sign. So that worked pretty well. What about multiplication by t squared? What if we had Laplace transform of t squared times a function? Well, t squared is just t times t, so we can write it like this, t times f of t. And then we can use the Laplace transform rule we just figured out to make multiplication by t on the inside. We can turn that into minus a derivative by s on the outside times the Laplace transform of everything that's left. But what's left this time is t times f of t. So we still have a Laplace transform left here to calculate, but we can use the exact same derivative rule to calculate it. So minus derivative with respect to s of, and then a t multiplication by t on the input of a Laplace transform produces minus derivative with respect to s on the outside of the Laplace transform. And then we can put all of this together. So the minus signs cancel, and this we have two derivatives with respect to s. So this turns into second derivative with respect to s of the Laplace transform of f. You can see we could do this again with higher and higher powers of t. Every time you increase the power of t, you get an extra minus sign and an extra derivative with respect to s. So if you have t to the nth power times a function, and here n is a positive integer, what you end up with is you get n copies of minus 1, so minus 1 to the n, and then the nth derivative with respect to s of the Laplace transform of f. All right, so that's not so bad. Let's use this in an example. And the example I want to look at is comparing these two Laplace transforms. So the Laplace transform of t times e to the t and the Laplace transform of t times the Laplace transform of e to the t. Now the reason I want to look at this example is because it's very common for people just encountering the Laplace transform for the first time. It's very common for them to think that that these two should be equal, that there's some sort of easy multiplication rule for the Laplace transform. But we'll see that these Laplace transforms are different. So let's work out this one. Laplace transform of t e to the t. We could use integration by parts along with other Laplace transform formulas that we have already figured out. But let's use the Laplace transform formula we just derived. So we have multiplication by t here. So that becomes minus derivative with respect to s on the outside. So derivative with respect to s of the Laplace transform of e to the t. But we know the Laplace transform of e to the t. It's 1 over e minus 1. And the derivative of, not e, s. The derivative of 1 over s minus 1 is minus 1 over s minus 1 squared. So then these minus signs cancel. So we get 1 over s minus 1 squared for the Laplace transform of t e to the t. Now let's work out this other one, Laplace transform of t times the Laplace transform of e to the t. So Laplace transform of t is 1 over s squared, and the Laplace transform of e to the t is 1 over s minus 1. And so we get 1 over s squared times s minus 1. Now comparing these two, you can see they just aren't the same, right? So this guess that maybe a product inside is the same as a product outside of a Laplace transform, that is not right. So if you, every time you're calculating a Laplace transform, you have to be careful about multiplication inside the transform. There's no quick and easy multiplication rule for the Laplace transform like there is for a sum inside of a Laplace transform, so be careful.